Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce Hossein Mobahi. He is joining us from UIUC. His advisor is Yi Ma. He's currently actually visiting us here at MSR about once a week, so if you want to talk to him at any point, let me know. He's hanging around and doing research here because his wife is currently actually working at Microsoft as well. Hossein has done a lot of interesting work. He's done some work in image segmentation. He won the Best Student Paper Award at ACCV and has a follow-up paper at IGCV on that work. He's done face recognition. One of my favorite works that he's done is on deep learning using temporal coherence. You should check that paper out. And today he's going to be talking about some of his more recent theoretical work, which he submitted to CVPR. And I'll let you describe it.
Okay, thank you, Larry. Hello, everyone, and welcome to the talk. So I'm going to talk about non-convex optimization with Gaussian blurring technique and continuation, and I'll discuss some of its application to image alignment as well. This is joint work with my PhD advisor, Ima, UIUC and MSRA, and Larry Zitnik from Building 99 at MSR. So the talk consists of two parts. At the beginning, I will just give you some basic definitions, working definitions, and then some preliminary results from theory side. And then the second half of the talk will be more about application to image alignment. Okay, so talking about optimization, we need to address convexity and non-convexity. We all know that non-convex optimization in general is not tractable, and because of that, there is always a pressure on engineers to try to model the problem as a convex one, even if the actual process is not very similar to a convex process, or write it down as a non-convex objective function and then try to relax it to a convex function. That is one way to deal with it, but if the actual objective function is far from convex, of course, this is going to be very crude and not very useful. But unfortunately, a lot of real-world problems are non-convex, so we cannot ignore this class of functions. And one good news is that real-world problems usually have some kind of structure and regularity, and they are not random. This means that even if they are non-convex, there is a possibility that if you exploit that structure in your problem right, then you can solve that problem efficiently. There are even examples, like even integer programming examples, that if you have some conditions on the problem, then although it's non-convex, but it can be solved efficiently. There is actually a vast literature on this, people trying to exploit different features in the problem. Here you can see some of the squares or difference of convex or many other. But today I'm going to talk about one specific approach that it also tries to exploit some structure, and that's the smoothness of your objective function. And it has been very popular. People have been using it in practice, but surprisingly, there's little theoretical understanding about fundamental issues with this method. And I have some preliminary results for this. I'm working on this theory, so this is a presentation based on ongoing work. So it's by no means a complete theoretical framework, but I think even the pieces that I have so far is interesting to the audience.
May I ask a question? Do you know whether this technique has been used in neural network optimization?
Yes. Yeah, there is an author, I think, Gorse, I don't know how. So Gorse, that's a very old paper, I think around 80s. So, yeah. Let's be precise about what we mean by smoothing. So smoothing happens in nature and in physics. Perhaps a representative example is from heat equation. Heat equation is simply a partial differential equation. Here you can see the definition of this partial differential equation. So if you set the initial condition, and if there is a boundary, if your space has a boundary, then you set the boundary condition, and then it gives you a solution. So you can say, okay, let's be concrete here. Let's say you have a bar, and then there is some distribution of temperature along this bar, right, at time 0. Now you leave this bar on its own, and this heat starts to propagate and spread across the bar, right? And eventually it reaches an equilibrium point where the entire temperature on the bar is the same. So let's define this function g in two variables, x and t, where t is time and x is the location on the bar. And let's say the initial distribution of temperature on this bar is denoted by fx. So that becomes your initial condition. Now, what this has to do with smoothing, you need to look at the solution, what the solution looks like. If you solve this problem, for the case that your space is unbounded, that gives the simplest form of solution. The solution will look like this. So this is essentially a convolution of your original function and a Gaussian kernel. If you just replace t with sigma squared, it will become more familiar to you probably. So I have a video here actually, which shows that if here, this is like the location x, and here is the temperature, and this is the initial setting. I just ran that differential equation to show how it starts to smooth this function. So very simple idea. But how can we use this in optimization? So in order to see how it's useful for optimization, let's play this video backward in time. So we start from a highly smooth function, but what we additionally do is that we find its minimizer and then try to trace this minimizer back to the original function. At each point, okay, we are in a local minimum, and then by the next infinitesimal change in the function, we try to follow that minimizer and basically follow that path up to when we get back to the time 0. So, and remember, this was the original function, and this red point is showing the minimizer you are tracking. So this function, of course, is not convex. It at least has two local minima that you can see, and one of them is the global minimum. But when you do it like this, you trace the minimum, it actually finds the global one for you. Okay. This idea, as I said, theoretically is little understood, but I can tell you it's very popular even across different disciplines. For example, in computer vision, which is my field, it's called graduated optimization. You can look it up. There's some explanation in old book by Zisserman and Andrew Blake. I think it's called visual reconstruction or something like that. And in chemistry, people call it optimization by diffusion equation. In scientific computing, it's called by homotopy continuation. And in engineering, sometimes it's called deterministic annealing. There are slight differences between them, but the core and the essence is the same. They start from a smooth function and then trace the solution. So it's surprising that despite its recognition, there is not much known about this problem. And here are just some of the interesting questions, yet very fundamental, that you might want to ask yourself when you work with this kind of algorithm. For example, the idea is that we want to make the objective function smooth. When is it useful? When you smooth it enough, it becomes convex, right? Of course, it doesn't happen for any kind of function. So you want to know for what function, if you push your sigma, the amount of blurring in your Gaussian, toward infinity, it starts to look like a convex function. So that's the first question. The next question is that, assuming that your function is asymptotically convex, you want to find its convex minimizer, right? That's your start point for this process. But as the problem gets smoother and smoother, it becomes almost, the objective function becomes almost like a flat curve. and highly unstable, numerically very unstable to apply any kind of numerical techniques for finding the solution even for a convex function. So it's not the best way to do it. But we hope that there is a closed form for that asymptotic minimizer that we can just get it explicitly without running any numerical procedure. The other question is, okay, what is the size of these asymptotic convex functions? Are they large relative to convex function? If so, how large? And then because we are tracing the path from the smooth function back to the original function, we want to know that this path is traceable. What if in the middle of path you see a bifurcation and then you don't know which way to choose, right? I'm assuming that this is a deterministic algorithm, non-recursive, so you don't want to branch. You just want one direct path back to the solution. And again, I would like to emphasize that this setting, this approach has very deep roots. It has connection to very fundamental forms of differential equation and fundamental processes in physics. So there should be something out there. I believe it's a very fertile, unexplored ground, and hopefully something will come out of this research.
You don't mention about the dimensionality.
Not yet.
I mean, the one you show one dimension.
Yeah, that's for visualization.
But in high dimensions, things will be much more difficult.
No, the concept is the same. Nothing changes about the at conceptual level. It was just for visualization purpose. Now we address some of these questions along the top. But before, again, starting, we have to be a little bit precise about what we mean by asymptotic convexity. So loosely speaking, that means if you smooth your function, by smoothing, remember I mean convolution with the Gaussian, and it has a sigma parameter that the larger, the smoother. If you push this sigma to infinity, then the function starts becoming convex. But more rigorously, what we mean is that for any radius m that you pick, there exists some blurring amount sigma star such that for any pair of 2 points that lie inside this ball, and for any sigma that is greater than sigma star, it satisfies the convexity condition within that ball. This is just a definition of convex function.
What's the G relation?
G is okay.
It's the heat equation.
Yes. So G is the, in other words, is the smooth version of your original function fx. So in f, it was only depending on x, but for G, it has two parameters. One is x, one is sigma. So when sigma goes to 0, it gives you f.
So sigma here is just it's kind of a smoothing parameter. So
yes.
The smoothing could be done heat equation or by some other mean, maybe.
Yeah, but for this talk, it's the same. So basically, for this talk, all the smoothing I'm talking about is just convolving your f with a Gaussian kernel. Okay. And that's the solution of heat equation. But you can explore other kinds of smoothing.
So just curious, for heat equation, it just happened that the exact solution will have that particular form.
Exactly, yeah. If it's an unbounded domain.
I see.
Yeah, like
So suppose for high dimensional heat equation, it will be just very Gaussian.
Yeah. So yeah. So this actually getting back to the heat equation. So here you have Laplacian operator, and that acts on multivariables. All right. Now a couple of simple propositions. So any convex function that you have under very mild conditions is also asymptotically convex. Very simple. You write down the definition of convexity for f, and because your kernel Gaussian is non-negative, it doesn't change the inequality, so you can multiply both sides, and again, you can integrate, and you get the definition for G. So from this, we know that at least the class of asymptotically convex function is as big as convex function under mild conditions. Now, the other thing that is, again, not very difficult to figure out is if you're talking about twice differentiable functions, then you know that the Hessian of that function at any point needs to be positive definite in order for function to be convex, right? So here for asymptotic convexity, again, you have similar definition. It says that if your sigma is large enough, larger than sigma star, then everywhere within this ball of radius m, it's positive definite. Now, let me give you a very bizarre example. To my opinion, it's a very bizarre example. So consider that function. It doesn't matter mathematically what it looks like. Visually, it looks like this. So it's almost flat and then goes down very quickly and then comes back up. Why it's important, it's very close to L0 norm. So people interested in sparse representation recognize that. Now, from convexity point of view, what's important about it, as you choose as you choose epsilon smaller and smaller, everywhere on the entire domain becomes concave function, except a very tiny region around this tip. And now I mark the regions that are concave by pink. So here you can see that it's almost like it doesn't exist because it's discretized by pixels, so it's like it doesn't exist. But what if you start smoothing your objective function? It changes to this, and now there is a tiny region you can see, white, that is convex, right? And as you increase the amount of sigma, the amount of blurring, this region of convexity starts to expand. And it just has no bound. So that's why it's called asymptotically convex. You can just make it convex for as large domain that you like. But the important point about this example was that your initial function, it was concave everywhere. So this seemed like very difficult for a convex relaxation type of thing. But it's actually asymptotically convex function. OK, that was a very good news. I'm going to give you a couple of more good news about these functions. So is there any sufficient condition, easy to check, that you can say a function is going to be asymptotically convex? The answer is yes. You just need to integrate the function, the original function, no smoothing at all, and look at the value of this integral. If it is bounded and if it is strictly less than 0, then it's asymptotically convex. So it's a very simple condition, and it's derivative free. So to me, it was very interesting. And as I mentioned earlier in the talk, because when you approach the asymptotic convex function, it becomes flat. So it's really difficult to find its minimizer by numerical procedure. So is there any closed form solution for the minimizer of that function? Again, to me, very interesting closed form expression exists for it, which tells you that it's just the center of mass of the function. So that if you want to derive this mathematics, I have to be like a little bit informal, because if first there's no time to go through all the details, and second it will become dry. So but my arguments here are very high level. They're not like you cannot consider them as complete proof. But if there was any question about more rigorous argument, please feel free to.
I just wonder whether this solution happens to be the same as, well, actually we know that this is the solution for minimum mean square error estimate for all the signal processing applications. So does it have any bearing? So if you want to minimize a mean square error of a nonlinear function, then the solution will be just exactly the same if the criterion is square error, which is actually convex.
No, I didn't know about that.
Okay.
Yeah, I'm not sure. Maybe there is.
Because you're convoluting with a Gaussian, right? The Gaussian just totally dominates when the parameter is high enough.
See, yeah,
it's
so
just like finding them. It's, you're trying to minimize kind of a Gaussian, pretty much, or maximum, right?
I see. So that may be the connection.
Yeah, that's the connection.
I see.
But can you just kind of just hand wave the proof of the top thing? I don't know. It's surprising. So why?
Yeah. So the way you can prove that is you write down the definition of G. G is convolution of f times your Gaussian kernel. Now you take the second derivative of that, and you can do it with in f or in the Gaussian kernel. We do it in Gaussian kernel, and then what comes out of it is two terms that depend on. I think it's something like this. So there are two terms that one is over, okay, I think it's like this. I think it would look something like this, and then again your Gaussian kernel. So if I want to be complete, you have this f of t here, and then k of x minus t sigma. and dt. Okay, so when you differentiate this kernel, you get this. Now, as sigma gets large, you can ignore this one, right? And also, this one is like a non-negative thing, right? So you can ignore that, and it just tells you it's negative of, and again, as k goes to infinity, it becomes like you're integrating over f alone, right? But with a negative sign. So in order for this guy to be positive, you want the integral of f to be negative, right? So this is, but you should work out the details, of course, because, yeah, but is it clear how are they?
This is pretty much the same truth as in minimum square.
Yeah,
If you ignore the first term, so they are identical.
Yeah.
Okay.
Is it clear? Okay.
So one thing about your negatives, it seems that if you can shape the function by a constant, then you would have more.
Yes.
And a function has a finite integral, for example. Could it be there?
Actually, we want the function to have a finite integral, because otherwise we cannot.
No, he's saying if the integral is finite but positive.
Then it's asymptotically concave.
Positive?
Yeah.
If
But what
if
if
it's
you-
positive, you just subtract the constant from the
Yeah, you
function.
just subtract.
No. But then it's not integrable on the entire domain. See what I'm saying?
Oh yeah, okay.
So if you add 1 to a Gaussian and then integrate it, it's no longer bounded. But remember here, I explicitly mentioned that we want the integral to be bound. And this is a sufficient condition. So you can find asymptotic convex functions that do not satisfy this. But this is handy, so you can easily test some class of functions. And here's a concrete example. So again, suppose f is that function. Again, its form is not that important, but it looks like this red curve. And it has one minimum here, one minimum here, and a maximum there, right? And for this problem, based on the things that I just told you, you can easily figure out it's asymptotically convex, right? You compute the integral, even it doesn't have to be precise. You see that it's negative, so it's asymptotically convex. And where's the asymptotic minimizer? Again, use the definition. You get so the yellow bar shows this point. And now here it shows different plots. So this is the original function, and this is a little bit smoother, and this is even more smoother. You see that the minimizer is moving toward this one, and it's also looking more convex.
So of course, I mean, once you do that, how do you map back the original minimizer for the record?
Yeah, we haven't got there yet. Yeah, this is So if you remember, there were a couple of questions listed. The first one was asymptotic convex, so we are only talking about that right now. So for now, I think based on the proposition I gave you earlier, you at least know about this under mild condition. But I'm going to give you even more good news. So again, these arguments are not rigorous for this talk, but at least it should communicate the idea. But more rigorous proof is available for those interested. So the measure of functions that are convex is 0. If you want to be concrete, we can limit our class of function to this one. So it's just one varied class of functions, twice differentiable. And then you know that the second derivative vanishes at infinity, and the second derivative is bounded by capital F everywhere. Now the argument is like that because it vanishes at infinity. So you can find some radius delta that captures most of the signal. You can make delta as large as you want, and then anything outside of it you set to 0. You don't care. So you can make this approximation to the original f double prime as small as you want, the error as small as you want, by choosing larger delta, right? So we'll work with just this one. Now this gives us at least a bounded support of this function. And everywhere, of course, on this function, we have also this inequality. Now, let's divide this bounded support region into n cells, equally spaced. Now, the chance of, what is the situation when this function becomes convex? When all of these cells have positive value, right? But if you look at each cell is just one evaluation of the function. So, because we're talking about second derivative, it's convex if at all these cells is positive, right? The chance of seeing a positive number in each cell is a half, right? Because we are saying that there is no preference in the sign. We just say the space, its magnitude is bounded, right? So it can choose either bound. So overall, the chance of seeing a convex function, meaning that all of these are positive, is half to the power of n, right? Now, as we increase this n to get closer and closer to the actual function, this density approaches 0, right? So you can say that from this rough argument that the measure of convex function is 0, at least on this function class. But what about asymptotically convex functions? Well, very good. Half of the functions that you pick from the space are asymptotically convex. And why is that? Because okay, here it needs to be double prime, I think. Yeah, you need double prime here in this. Because again, there is no bias in our assumption on the class of functions. So half of the functions have their second derivative less than 0, their integral, and half have positive. And you know that as you make the function smoother, by the same argument, it becomes more closer to its integral. So it's like half of the function are asymptotically convex. So these are, I think, very good news. One other thing, maybe somewhat related to your question, is that now, suppose we have asymptotic convex. Suppose we found its minimizer, asymptotic minimizer. Now, the procedure required us to follow the path back to the original problem, right? How do we know that we can do this? Because if somewhere along the path there is a choice, then we are confused. We don't know which path to take, and we don't want to branch, as I said. So we need to avoid this kind of situation. And mathematically, what that means is that on the smooth function, we don't want the Hessian to be singular anywhere, right? Now, so again, you can do that with some manipulation here. First, you can derive the path of minimizer. It's very simple to derive this one. I think it should be clear. Just write down the equation for points that satisfy the stationary point, and then differentiate that with respect to sigma, which is like time here, and then you rearrange terms and you get that, right? Now, in order to make sure along this path you don't see any singularity, you need to make sure that your Hessian remains positive definite along this path, right? And at asymptotic minimizer, we already know that the Hessian at that point is strictly positive definite, right? I mean, all the eigenvalues are strictly greater than 0, right? So you want to maintain that situation. You want the and let's say, okay, lambda here shows the smallest eigenvalue, okay? You want to see what is the evolution of this eigenvalue over time, right? And then see if it's getting smaller or larger, in which direction it's moving. You don't want it to go down, right? Given the eigenvalue itself, can there be said anything? Is there any relationship at all between this eigenvalue and its evolution in time? Yes, there is. I cannot get into the details because of time, but here I just say you need to use two things. One is the property of heat equation that relates this operator to this operator. So differentiation in time becomes Laplacian in space, and therefore you can read this again. If I have information about second derivative, the eigenvalues, can I say anything about fourth order derivatives? And again, yes, you can if the function is smooth enough. Just use the negative definiteness of Laplace operator. And just to give you an intuition for those who are not familiar with that, why is that the case? So if a function is very smooth, let's say it just consists of one sinusoid, right? Let's say sinusoid, sine of x, right? So this is your f double prime. Now I differentiate this twice more, and what I get is minus sine of x, right? So it's just the flipped version. So there is a very coupled relation. But as you add more terms to this, like high frequencies, then this is not quite the case. But as long as your function is smooth, so these terms are dominant, then you can relate these derivatives. So by taking, yeah.
I have a question. In your previous slide, you had this nice animation that showed that this little kind of concave bump magically appears exactly where the minimum of the initially asymptotically convex smooth thing is. And this is why you got this branching behavior that you're trying to avoid.
Right.
Now it seems like if you had just added a little bit of noise, this is a singular point. You could have made another animation where the bump just shows up a little bit to the right or to the left, and you would not have ever had this conflict
Yes.
where to branch. And
Yes,
I think
that
a perturbed
yeah.
analysis or a little bit of noising could solve this, right?
Yeah, I get your point, but the goal here is not to just randomly pick. Okay, in this maybe it's misleading because both of these are symmetric. Let's say one of these actually becomes deeper eventually, right? So you want to follow that path, and this one stays like a local minimizer. So if you want to like choose one direction by chance, then maybe you choose the wrong one, right?
I'm not saying choose one by chance. So let's take a step back in that case. Proving that your entire trajectory has no branching points is weaker than proving that you'll actually converge to the minimum of the non-convex function, right? I mean, you could have something that appears very, very far away from where you are, which turns out to be the global minimum. So that's a separate issue. So all we're saying now is we're asking for a lesser thing. We're not actually trying to find the minimum of the non-convex function. We're just trying to prove that as we do the smoothing thing, we never hit a conflict or a fork in the road that we have to choose. And I'm saying just to avoid that, it seems like a perturbed analysis, namely showing that this will happen with measure zero, or adding a little bit of noise to the function itself will prevent this. It seems to prove that, right?
Yeah, but as I said, this is not the entire goal. So this is one condition that we want, but we need to have some control over it. So we need to basically say which path it chooses so that it gets to the global minimum. So I haven't discussed that yet, but there are different ways that you can control and prevent this. One is that, but what we really need for making sure that this path leads to the global minimizer, we need something more than like local perturbation or adding noise, because by adding noise you're not using the assumption that which direction is better for leading you to the global optimum, right? It's just noise. But we can discuss that later if you want, because I think I need to get to the application part. Actually, I'm done with the theory, so if there was any question, I'll be happy to answer after the talk. But now let's get to the application of this idea. So it's image alignment. It's a very fundamental problem in computer vision. If you do structure from motion, view invariant recognition, or tracking in videos, you usually have to hit this problem. Now, there are two major approaches. Actually, if anyone wants to read a little bit more about alignment, there is an excellent tutorial by Rick Zelinsky here, and all the details are there. But there are two major approaches that you can use for alignment. The first one is feature-based. So you select a bunch of sparse feature points and then try to make a correspondence between them, and then use that to infer what is the geometric transformation between the two images. And the other one is called intensity or direct method, and that's you just subtract the two images, all the pixels get involved, and then you get a residual, and then you try to minimize this residual. So find the alignment that minimizes this residual. So intensity-based method seems more tempting because it uses all the information in the image. But in the first one, you are throwing out a lot of information. And so this one seems to be richer in some sense. But unfortunately, when it comes to practice, usually you have a lot of local optima. So it doesn't help that much. Now, again, to get you familiar a little bit to the setting, let's say we have a very simple problem, alignment. So F1 and F2 are two different images, and then they're different by displacement d. So the task of alignment, we can just formulate it like this: minimize d such that minimize this objective to get the optimal d. Right? Now, this is non-convex because f is out of our control. It's an image, and it can look a very crazy function, and therefore d can look very crazy function, right? So you need to somehow get away with it. One way is you linearize your f with respect to this optimization variable. In this case, it happened to be d. And first order Taylor, you get this, and then plug it in there. Now it gives you a convex quadratic function. You can solve it even in closed form. And then you get some d hat. It's just an estimate. And then apply this to the image. But remember, there is an approximation here. So if this approximation is poor, then this is far from your true solution, right? And then according to Taylor's remainder theorem, you can bound this difference. So this one is obvious because here we are linearizing around the origin. So the larger d, the worse it gets. And this one depends on higher order term. Actually, it's the largest eigenvalue in magnitude of the Hessian. So you want that to be small as well. Well, that depends on the image, and what if it's not small? What you can do? You can smooth your image. You can actually blur your image, and the effect of this is that lambda, capital lambda, will become small, and helping you so the d estimate of d you get is closer to d star, right? But again, there is a problem here because as you blur your image, you lose some of its details, right? But you can do this iteratively. So this is called lucas-kanade algorithm. So you start from a very coarse blur and make the alignment, and then apply that alignment to make things a little bit closer. Now your d is now reduced a little bit because now you're working in a smaller domain. So you can reduce the amount of blur because we want this total thing. Sorry, it's previous slide. So we want this total thing to be small. So as you optimize over d and d gets smaller and smaller to the desired value, then you are allowed to increase this one, and that can happen by like making it less blurred, the image. Okay, there is even a proof that this idea works well. It can recover the correct displacement as long as we are talking only about displacement. But I have seen people using it even for motion models that are not displacement, and that is wrong. And it's easy to see that. I mean, by wrong, at least it's not optimal. So let's say that we change the problem setting. Now instead of displacement, we are talking about scaling. So F1 now, okay, we have F1 Sx. So this is the objective function. We have F1 Sx minus F2, and then we square this and then integrate it. So again, we can linearize it. We get this form, and okay, we can find a closed form solution. It's convex quadratic, and look at the error bound. This is very important. Now in the error bound, you still have that capital lambda. You still have the deviation of this variable from the linearization point. But this term appeared here, which shows that the quality of this error depends on the location in image that you do the linearization as well. So in other words, as you get farther and farther from the origin, this approximation becomes poor. So suggesting that if you want to do any kind of blurring, it should be more intense and aggressive for points farther from the origin, right? So remember this point here because we will get back to this. I just wanted to mention lucas-kanade algorithm. So we need some kind of blur that's spatially variant. But in lucas-kanade algorithm, what it does, it just blurs the images with an isotropic Gaussian. So every region is treated equally. But let's look at the eye, human eye. Let's see what it looks like there. So there are some color receptors called con, if I'm pronouncing it correctly. And this is the density of those points. This is the center of the eye, and as we go towards the periphery, you see that the density rapidly decreases. The implication is that whatever you see at the center of your, in your fovea, it has the highest quality, and then as you move toward the periphery, then it becomes blurrier and blurrier, right? So at least from biology, there's an evidence that you need this kind of spatially varying blur. Also, people in vision have heuristically come up with ideas like Berg and Malik, based on their intuition, they developed some blur kernels that are not spatially invariant, but it's just heuristic. But today, we are going to derive these kernels in a very principled way for the first time. So, again, to be concrete and illustrative, let's take the same example. It's 1D scale alignment. That's the actual task. And what traditionally people in vision do is that they smooth the signal. So this convolution is over space X, and then try to solve it by lucas-kanade algorithm. But what I am suggesting today is to smooth the objective function, because that's where you want the minima, local minima to disappear, right? So this should be really your goal. And let's look at the landscape of this optimization objective to see what it looks like. So the signals are these. One blue, one red. I hope it's visible. Very simple functions. And they are just flip mirror of each other. Okay? So the optimal scaling is -1, so that you flip them. Now, by signal smoothing, you get this picture. Now, what is this? So this is where you have the highest blur, and this is your choice of scale factor. So it has 2 local minima here. So as you make it blur enough, you still have 2 local minima. So you have to choose them, choose one of them randomly, right? And then if you trace the path of that back to the original by reducing the blur, there is a chance. Either you hit the global minimizer or you hit the local minimizer. This is for this one, lucas-kanade. But if you blur the objective function, then there is only one start point. And for this particular example, it's actually the one that leads to the global min. There is another path that starts somewhere in the middle of the road, but we never get that because we...
Depends on how you blur. If you blur it the other way, would it go the other side?
What do you mean by the other way?
No. Here, when you trace it down here, right, you just happen to trace it on the left. I suppose that's due to the same problem that you mentioned earlier about bifurcation. Maybe I misunderstood.
Well, no bifurcation happens here, either on this one or that one. There's no bifurcation.
So
but this is...
Under what condition does it trace back to the wrong local optimum?
So that's the most difficult question. If you remember, I was listing a bunch of theoretical results that we have for this problem. And that is something that I'm working on still. I don't have concrete results to present, but I really hope that we can also get at least some conditions on that as well to connect really that theory to the application.
So basically, after you do the blurring and then you find the global optimum, that's empirical finding.
Yes, yes.
So maybe for different example, you may show
yeah.
the other way.
Yeah. Okay. Now, what is the practical challenge here? Well, if you want to blur your objective function, let's say your transformation is homography on plane. So you have 8 degrees of freedom. That means you need to evaluate an 8-dimensional integral, right? Because this convolution is going over the parameter space now, right? And that can be expensive. So the question is that, is there any alternative 2-dimensional function that if you compute this integral transform in 2D, it becomes equivalent to this 8-dimensional integral for smoothing, right? And fortunately, that's the case, at least for most of the transformation we care about. And I call this guy the transformation kernel. And how do I derive it? Well, you use Fourier analysis and get to a very simple proposition here. And based on this proposition, if you plug in tau to tau is your transformation model. So tau takes a point x and then returns another point y, for example. So if you plug in your tau here, then you get at least the Fourier form, and then you need to convert it back to the spatial form. And the proof of this proposition is simple. You use just Fourier representation and then Parseval's theorem. And if you do that, for these transformation, you derive the corresponding kernel. So, for example, translation is x plus d, and this is the kernel you get. Also, you can see for homography, this is the transformation, and I didn't put these because these are long expressions, but this is some exponential form, and this is some rational form. And this is a visualization of some of these kernels. So these two are for affine, those two are for homography. Now, again, the point here that I want to emphasize is that these kernels, when you want to compute their integral transform, they are 2D integrals, not 8-dimensional integral. But they have the same effect as integrating your function over that 8-dimensional space. So brings some efficiency. And of course, I cannot go through the details of the derivation here, but I can at least tell you two things that you can check the correctness of them, two necessary conditions to check the correctness of them. One is that because original intention was to smooth by a Gaussian kernel, so it has to obey properties of heat equation, right? So first, it needs to satisfy the relationship between Laplacian and differentiation in sigma. And second, you want, as the smoothing amount goes to 0, you get the original transformation. And if you test that on this table, you see that it's the case. Okay, so now in general, if we are not talking about just a particular transformation model, you can write the correlation. So correlation is another measure like L2 error that you can use for alignment. You try to maximize it. So if this is your original correlation objective function, you can start smoothing that objective function with this Gaussian kernel in the parameter space, and then use that kernels to make it an integral over the space of x. This is the important point here. So now this became 2-dimensional. And then there is a simple algorithm that just follows the path of the minimizer or maximizer. Now, perhaps we're getting close to the end. One point that is worth mentioning is, again, getting back to lucas-kanade algorithm and see how it compares with these kernels. So it again shows that for translation only, what you get, if you plug in the translation kernel, then what it looks like is that you are actually convolving your image with an isotropic Gaussian. So again, this is re-emphasizing that if motion is just translation, then yeah, using just a isotropic Gaussian with fixed sigma is okay. But once you move to other transformations, say affine, that becomes an integral transform that is not necessarily a convolution, and you need to do that, and it's spatially varying. So experiments are very limited because these are really preliminary results, but here you can see the results of alignment. So these are the images we use for alignment. And this axis shows how much transformation was drastic. Then the transformation class was homography. So this one was the most difficult because it had the largest homography change. And these curves show the correlation coefficient that the algorithm converges to after alignment. So the bigger, the better, right? And you can see that for no blur, red, or Gaussian blur, they do almost similar, and they are way below when you blur the objective function. Of course, all of them become worse as you make the problem harder, but the point is that this is always doing better than others. So that was all, and I just want to acknowledge Vadim and John for their helps, and thank you very much. I think we have 5 minutes if there's any question.
Any additional questions there?
Yep.
What happens if you use something other than Gaussian?
Other than Gaussian, no. And the reason is that I really leverage the property of heat equation for that. If you remember that discussion about traceability, so I convert the evolution over time to Laplacian, and then that's very important because now everything becomes static. You don't care about time evolution now, and then you can use that to say something about how you're losing convexity over the curve and stuff. But of course, you can consider other, but that's probably more difficult, I suppose.
I suppose suppose if you use other kernel function, you won't be able to get such a simple solution as the center of gravity. That gives the solution for asymptotic, the center of gravity solution.
If it's other kernel?
Yeah, other kernel, for example, if you use Laplacian kernel rather than Gaussian kernel.
These kernels are not Gaussian.
I'm talking about this. I mean, one of the solutions you have for asymptotic convex is the result is the center of gravity, right? So
you're talking about that example?
Center of
this one?
Yeah, correct.
So
if you use the other kind of kernel to do smoothing, you probably won't get that.
Well, I'm not sure, as I just said. I only explored Gaussian, and the reason was that it has a lot of nice property that makes the analysis easier. Yeah. But I think, you can, but it will be more difficult.
No, I'm saying that if you use a different kind of kernel empirically, do you show that maybe some different solution you might get?
I didn't try. Yes.
So you derived some of the kernels for particular types of transformations, but there's a very large range of possible transformations, and some of them are difficult to even parameterize. So how about trying to learn these kernels from examples of images? With ground truth, you know the alignment, the images are given to you. Now you're supposed to find kernels that are going to have the optimum at the right point.
Right. Well, I think in principle that is doable. But I believe you have to do it like by some numerical procedure. I don't think you can do much by closed form because it highly depends on the form of your data, and if you cannot make that much of assumption on your data, then it can be anything.
It's a step back because you're not going to guarantee anything. It's still just learning procedure. But I'm just wondering, in comparison, does that, like for the examples that you can derive things with the learning procedure, get the same kernels anyways, and then for some other things where you can derive things, the learning procedure will give you something reasonable.
That's some experiments that is very interesting to do. Especially I like the first one to see if we cast this problem as a learning task and then limit the transformation model to those that we know their kernel, then will their kernel converge to the same thing? So that will, because they are a little bit different, I think, in terms of their objective. So if you use learning one, I think the goal is eventually, do you want to do classification? I mean, is the optimization criterion optimized for?
Well, you want to optimize for
reconstruction or
for whatever your function was, right? You're trying to find the blurring kernel that's going to minimize the function at the right point, right? But you're given examples of images with ground truth.
Yeah, that's definitely a very interesting experiment to do. But I know a lot of, through informal chat with people, including Larry and with you, you all had this observation that based on empirical results, you got something similar to these blur kernels. So, but doing, I think, a very conclusive experiments on that is very interesting.
Well, I think, in practice, you really want to know, there's 8 degrees of freedom in homography, right? And do you want the standard deviation amongst those 8 degrees to be all the same? Probably not. Translation might have a wider variance in scale, etc. So I think through training data, you'd actually learn the standard deviation of those 8 parameters, and then use that, plug it into the thing's model, and that will give you the right kernels for that. So you wouldn't do it truly non-parametric. You do it in a, you really just learn that there's a small subset of parameters.
Yeah, I think you're referring to regularization, right?
Yeah, well, it just makes
so in the CVPR paper, we don't know yet if it gets accepted, but if it gets accepted, you will see. So we had one more thing called regularization of the solution, and that just adds some prior, but we use very simple prior, just identity transform. So no special bias, but we use that just to prevent converging to very weird transformation. And I think what Larry is suggesting is that now with learning, you can more accurately model that prior because that's specific to that data. But because of time, I couldn't talk about regularization here. Thank you.